Corey, the person who made the most about this meeting, so I'm gonna make sure you get one.
I
Shane,
think
you
you
got
left
any more?
yours right here, Shelley.
That's an extra one?
Only one extra? Oh, that's not good. Yeah.
One swilling like
Do you need one as well?
I do.
How about if you take, boy, this is,
Trying to get them all passed out,
do you
sir.
need one?
Have one. Everyone should have one.
So, the purpose for this experiment is to calculate GM. And really, its purpose is to calculate KG. Here's a vessel floating in the water. I know where the keel is. And I don't know where M is. I'm just going to put an M up there. And I don't know where G is. They're both a big question. And shortly in the lab, you're going to ballast this vessel and will further not know where G and M are. However, the hydrostatic properties for a given draft will give you what of those values besides K? That's a
K.
question.
KM? Oh.
KM, right. Recall, and you might not recall, but hopefully you can recall that one of the hydrostatic properties you can pull off of SPE is KM, height of the metacenter, for a given draft, based on a draft. So you're going to draw the ballast this vessel and record the draft for an F. And then look up KM in the hydrostatic property. Good. Now next we're going to do the experiment called the incline. And this is an experiment that is done on real ships after they're built. We don't know where the center of gravity is on a real ship. After it comes out of the shipyard, it's floating. The naval architects set up specific conditions so the vessel's not being pulled one way or the other. And they apply this equation. GM is equal to WD over delta tan theta. So what they do is they take a weight and shift it a certain distance and cause a certain angle of list or heel?
List.
List. Good. Everybody said the right answer, for those who said. And so you record the angle and take the tangent of it. You know your displacement from where?
Hydrostatic properties.
Good. Hydrostatic properties will tell us the displacement as well. So we know that number. And you know the weight that's moved, and you know the distance it's moved, and you calculate GM. But the way you calculate GM is you don't just simply do that equation a bunch of times, like the lab data. But instead, you set up a graph that will look like the way I suggest you do it in your handout is the x-axis is tangent to theta, and the y-axis is WD. And when you have this data, you're going to collect this data and this data, and you're going to plot it. So for a large angle, do you think it's going to take a large distance to make a large angle?
I will.
Show of hands that it's going to take a large distance to cause a large angle of list.
A larger angle.
A larger angle
Yeah.
caused by a larger shift in the weight, okay? So that means you're going to be out here, out here, out here, out here, and you're going to find a graph that looks something like this, where this is, say, starboard, and this is port, okay? Something like that. And you're going to plot 8 data points, some of which should be fairly close to 0, but not quite. And if you take the slope of that line, is equal to rise over run, which is the change in WD, and the change what?
Tangent theta?
Tangent theta. Good. And if you take that and divide by something, you're gonna get GM. What do you think you divide by? Displacement. If you take the slope of the line, divide it by displacement, notice this is the slope of the line. Change in y or change in x. That's the slope of the line. Divide by displacement, you get GM. And that's how ASTM wrote the procedure that the Coast Guard requires that all ships have done after they're built. Or not just after they're built, but after they have maybe significant ship alterations. Like a new radar, a new ballast system,
Air conditioning.
new air conditioning system that significantly affects the expected center of gravity. So that will give us GM. And then Kg, which is the ultimate purpose of this experiment, is Km minus Kg. All right? Whoops.
Oh.
Thank you for looking quizzical. That fixed my problem. Now that's Kg with this weight on board. And this weight on board a ship, if the ship is, say, I did this on an aircraft carrier 1,000 feet long, ship weighs about 100,000 tons. We had bricks moved around by cranes. The bricks were about the length of this table from here to there. It's about 20 feet long. And the bricks were about this thick, and they're about that wide. So they weighed literally a ton, or maybe multiple tons. And so the cranes were moving these things around on deck, and you calculated Kg with that incline weight, with the incline weight. And I can guarantee that an aircraft carrier doesn't drive around for the rest of its life with those big trip hazards on deck. And so we have to calculate the Kg without the incline weight. And some of you have spoken so far, and some of you have not. So if you have spoken, don't answer this question. If you haven't, start looking around and seeing if your classmates are going to answer it for you. And little by little, I'm going to narrow it down so everybody gets to answer a question. So the question is, how do I calculate Kg without the incline weight? We all avoid eye contact very quickly. But you already said something. Why don't you take a look at your equation sheet?
Use the weighted.
But don't say anything, I think you said something too, right?
We would use the sum of moments divided by the displacement for kg.
Correct,
Kg
good.
fine.
So what Morgan said is that Kg without the incline weight is going to be equal to the sum of all the individual weights times their individual kgs divided by the displacement final. And what that will be is the displacement initial with the incline weight with, I need a little bit more room. It will be Kg without incline weight is going to be equal to the displacement of initial with incline weight times the Kg that you just calculated,
Oh, okay.
plus or minus. Now here's another question. If you haven't answered a question, here's another one you get to answer. This is a question that hands work best for me. Plus or minus the incline weight. You already said something. I'm glad you're answering the question. That's an easy one, right? You're done. Isn't it nice to know that I'm not going to call on you now? Yeah, you can go back to sipping on Alex's coffee or spacing out. So it's going to be minus the incline, the weight of the incline. Times its Kg. And we're gonna measure where that is, and we'll know the height of that block. Kg of the inclined weight. Divided by weight initial minus the weight of the inclined weight. And that's kg without the inclined weight. And that's the whole purpose for today. Calculate kg. I'd like to remind you of why it's important to know kg. Here's another question for those who haven't spoken yet. Say why it's important to know where kg is. Hands work best, so I can make sure that those who have answered don't. Corey, you can space out now, right? Safely? Who understands the question? Show of hands. So not everybody understands the question. I'll paraphrase the question. Why is it important to know kg? Why is it important to know the center of gravity? You already said something.
So you can determine GM.
We already know GM. We already calculated it. We calculated GM to get kg. Why do we want to know kg? Not to know GM, because we already know GM.
To know
All right, I'll
where
give you a
to
hint.
load stuff.
What?
To know where to load. Like if you want to lower, you have to lower below G.
Yeah, exactly right. What Shane said is if you know where kg is, center of gravity, say 30 feet above the keel, and if you ever add weight 20 feet above the keel, did you make the vessel more or less stable?
Less stable.
More stable, because you added weight below kg and you lowered the center of gravity. If your center of gravity is 30 feet and you add weight at 40 feet, did you make the vessel more stable or less stable?
Okay, then.
It's less stable because you added weight above kg and you raised kg. So, one of the two numbers I suggested you have in the back pocket whenever you walk on a ship is to know where kg is. Then you know instantly if you ever add or remove weight, if you're making the vessel more or less stable. Good thing to know. Not associated with this, but what was the other number that I suggested you know that you have in your back pocket? Johnny?
LCF,
LCF. And why LCF?
because you can determine where the center of flotation is, and that has something to do with your, what's the word I'm looking
So you can
for?
keep the ship
Trim,
balanced.
trim.
So if you know where LCF is, and if you ever add weight forward of it, you know the bow's going to go down. If you add weight aft of it, you know the bow's going to go, the stern's going to go down. So those are two good numbers to know where you can do everything in your head. Making the vessel stable, making the vessel trim. All right.
Is that why whenever those ships are across the harbor over there and they're unloading, they're trimmed back so far because they have so much weight behind the LCF because of machinery?
Yes.
Okay, so they're made to have all the cargo forward of LCF, or most of the cargo forward of LCF.
Yes.
Okay.
Good question. Now, were there two questions associated with why it's important to know KG? I don't remember if I asked for two questions, two answers. This one, okay. So that's the whole purpose for today is to calculate KG. And there is, one of the requirements in your handout is to go over and read the ASTM number, umpty clutch, which is about 30 pages. And I'd like you to read it enough to digest what it says. And I'll give you a hint as to sort of things that you want to pick up on. It's an experiment on a real ship. And it's going to tell you when you run this experiment on the real ship, the ship is going to be tied up to a pier. It's already built. And you want to make sure the mooring lines are slack. Why? Because if the mooring lines are slack, it's tugging on the ship to the pier, and it might be inducing a list, affecting the accuracy of your incline angle. Another thing that you have to do, so mooring lines are important. The other thing you have to do is measure the wind. Because if there's some temporary external force, if it's on a windy day, it's going to give you some artificial angle of heel. And you don't want it to be affected by that. So it has to be a fairly calm day. Another thing you have to do is check the current. A lot of shipyards are in rivers, and the current's flowing, and it might be pushing on and inducing a temporary external force, giving you an angle of list or heel.
Heel.
Heel. Current has to be checked. The depth of the water. Why in the world do you want to know the depth of the water? Now this is getting where I'd like everybody to make sure they participated. So this is where you put your hand up if you haven't answered a question yet. This is where you get to. And hands are best. Who hasn't answered a question yet?
Oh,
Put your hand up if you have not answered a question yet. Everyone has? I didn't think everybody has, but okay. Why do you want to know the depth of water, Alex?
Well, you don't want to make sure when you load, if the keel hits the bottom, kind of ruins everything.
Yeah, if the ship is sitting on the bottom, it's going to ruin everything. You might be moving weights around and nothing's changing because the ship is just stuck in the mud. And you want to make sure it's not. Okay? Another thing you're going to want to do is check the salinity of the water. And you have to be pretty accurate in that measurement of the salinity of the water because that affects the draft marks. And the draft marks affect your expected displacement with your hydrostatic properties. So you have to take into account the salinity of the water. Another thing you have to do is keep people from moving around. No movement of people or things. So you have to sound tanks, you have to know how much cargo is on board, to tell everybody, freeze, don't move. Well, actually on a big old ship you can move a little bit, but you don't go walking from this compartment 30 feet over to there. Everybody stays relatively put. And then you run an experiment, it tells you you have to collect 8 data points to make this graph that has 8 data points, 1, 2, 3, and then 2 around here. So there are going to be 8 data points you plot. And it has to be certified by the Coast Guard, and then you get a stamp saying this is your KG. Sort of interesting. Was anybody involved when they did it on the rudder a year or so ago? We did it on the rudder at the
I do
pier.
remember
2 years
doing
ago.
it.
Yeah. So every ship gets it done. All right. Oh, one other sales pitch for this is that one of the graduates from this program who went into the license option went out, and his first job was to be in charge of an incline of a ship. And he said that it was exactly like what we talked about in class. So that's kind of cool, you know, to know that it's real life stuff that we're learning, and you might be responsible for it. How will you know how to do it if you have to do it in real life?
I'll call you.
No.
Follow ASTM.
Follow that ASTM. And what is the number of that ASTM? I have it at the bottom of your handout.
1321.
Yeah. It's in the library, and I think you can very easily find it on the internet. It is, the way it works is the code, CFRs, Code of Federal Regulations, say that the Coast Guard has to make sure ships do this. CFRs say, or the Coast Guard says, okay, you guys do it, and they say it via what's called a NAVIC. And then the NAVIC tells ASTM how to do it. All right, then enough said, let's go do the experiment. And so Spencer, will you record this part? And this is where everybody should be participative. Participatory.